21 systems out of 22 are failing. On a humid morning over Indonesia, the world's largest passenger jet, a Qantas Airbus A380, is rocked by a massive explosion. A tiny manufacturing defect in a single oil pipe has triggered a catastrophic engine failure, sending shrapnel through the wing like a shotgun blast. 469 lives hang in the balance as the crew is bombarded by over 100 emergency checklists. They are flying a digital ghost that refuses to shut down. Where are you watching from? Comment below. This is the incredible story of Qantas 32 and the expert trap that almost erased a super jumbo. The crisis of November 4th, 2010 began with a sound like a double cannon blast. Qantas Flight 32 had just departed Singapore's Changi Airport. In the cockpit was an unusually high-powered team, 5 pilots in total, including Captain Richard Champion de Crespigny and 2 senior check captains. Between them, they held over 70,000 hours of flight experience. This overqualification would be the only thing that saved them. The cause was a microscopic error born in a Rolls-Royce factory. An oil feed stub pipe inside the Trent 900 engine had been drilled unevenly, leaving one side dangerously thin. As the A380 climbed through 7,000 feet, that thin wall finally succumbed to fatigue. Oil sprayed into the 500 degrees Celsius engine core and ignited. The resulting internal explosion shattered an intermediate pressure turbine disc. Rotating at thousands of RPMs, the heavy metal fragments became supersonic missiles. They sliced through the engine casing, through the wing's structural spars, and severed the massive bundles of wiring that act as the aircraft's nervous system. The pilots were suddenly staring at a red screen of death. The electronic centralized aircraft monitor, ISAM, began scrolling through failures at a rate the human eye could barely follow. The green hydraulic system was dead. Half the flight controls were unresponsive. The auto throttle had vanished. Most terrifyingly, the crew had no confirmation that their fire extinguishers had even discharged. In the cabin, passengers looked out to see fuel geysering from the wing and a small fire burning inside the structure. But that decision would have been enough to destroy most people. What happened next made everything before it look minor. As the A380 circled over the city of Batam, the crew faced an agonizing choice. If they landed immediately, they might lose control on the approach due to damaged wing slats. If they stayed up to troubleshoot, they might run out of fuel, or the wing fire might weaken the spar until the wing snapped off. If you're finding this breakdown of high-tech crisis management vital, hit the subscribe button now. We analyze the invisible triggers of aviation history every week. Captain de Crespigny realized they were falling into an information trap. There were too many failures to process. Drawing inspiration from NASA's Apollo 13 mission, he ordered his crew to invert the logic. Instead of trying to understand what was broken, they would list only what was still working. They discovered they had only one functioning thrust reverser and a 65% reduction in roll control. To test the plane's handling, de Crespigny performed a control check at high altitude, simulating the landing configuration. He needed to know if the plane would stall before he committed to the final descent. The math was grim. A senior check captain used a laptop to calculate the landing performance. The result, on Changi's 4,000-meter runway, the heavy, crippled jet would require every single inch of pavement, leaving only 130 meters, about the length of a football field, to spare. There was no room for a soft landing. They had to plant the plane on the ground to trigger the remaining brakes. She thought she had won. She had no idea what Thomas was already putting in motion. The approach was a masterpiece of airmanship. De Crespigny hand flew the 400-ton giant, bringing it in at 1,400 feet per minute, nearly double the vertical speed the landing gear was designed to handle. Just before touchdown, he executed a military flare, pushing the stick forward to rotate the plane around its center of gravity and cushion the impact. The Super Jumbo slammed onto runway 20 center. The tires screamed, the single reverser roared, and the brakes heated to a staggering 900 degrees Celsius. The plane came to a halt with just 150 meters of runway left. The 440 passengers erupted in applause, But the nightmare wasn't over. As fire crews rushed to the plane, fuel was still pouring from the wing onto the white-hot brakes. De Crespigny ordered all engines shut down. Engines 2, 3, and 4 died. But Engine 1, the outboard engine on the far left, ignored the command. The explosion had severed its control cables. The engine was effectively decapitated from the cockpit's brain. For the next 3 hours, passengers were trapped on a plane with a running jet engine and 900-degree brakes while fuel leaked nearby. An evacuation was too risky. The slides would blow into the engine intake. The pilots tried everything, pulling circuit breakers, cutting fuel lines, even reconfiguring the software. Nothing worked. Finally, the fire department had to drown the engine, pumping thousands of gallons of water and foam directly into the intake until the machine choked to death. But what Thomas did next, nobody saw coming. Qantas Flight 32 is widely regarded in aviation safety as a successful failure, an incident where multiple catastrophic risks occurred simultaneously. Yet the aircraft was safely recovered through exceptional crew performance, system redundancy, and disciplined decision-making. On November 4, 2010, the Airbus A380 operating from Singapore to Sydney experienced a catastrophic failure in one of its Rolls-Royce Trent 900 engines shortly after takeoff. A turbine disc inside the engine fractured, causing severe structural damage, system failures, and multiple cockpit warnings. Despite the seriousness of the situation, the aircraft remained controllable. However, the event triggered a cascade of over 50 system warnings, ranging from hydraulic faults to fuel imbalances and flight control degradation. This is where the concept of cognitive tunneling becomes critical. In high-stress environments, pilots can become fixated on one set of warnings or procedures, potentially missing more urgent threats. In this case, the crew had to rapidly interpret conflicting data while maintaining overall control of a heavily damaged aircraft. The crew's experience played a decisive role. Instead of becoming overwhelmed by the complexity of alerts, they prioritized core flight parameters, maintaining altitude, speed, and control, while systematically addressing secondary system failures. Their ability to avoid cognitive tunneling and maintain situational awareness is one of the key reasons the aircraft was safely returned to Singapore. Investigations into the failure revealed a deeper engineering issue. A misaligned oil pipe in the engine's manufacturing process had gone undetected, eventually leading to oil leakage and internal overheating. This defect ultimately caused the turbine disc to fail. The discovery triggered a global safety response, including the grounding of Airbus A380 aircraft powered by Trent 900 engines until inspections and modifications were completed. The engine manufacturer, Rolls-Royce, implemented significant design and process changes. Manufacturing tolerances were tightened, inspection procedures were enhanced, and a revised design for oil feed pipes was introduced across the fleet. Additionally, software-based protections such as overspeed detection systems were improved, allowing the engine control unit to shut down a failing engine before catastrophic disintegration could occur. This is where the expert trap becomes especially important. In this case, the failure was not initially caused by pilot error or operational negligence, but by over-reliance on automated manufacturing systems. A drilling process used in engine production had been slightly misaligned. Over time, repeated reliance on automated precision created a false assumption that no manual verification was necessary. The system itself became the expert, and human oversight gradually diminished. The incident highlighted a critical aviation principle. Automation improves consistency, but it cannot replace verification. Whether in manufacturing or in the cockpit, blind trust in systems creates hidden vulnerabilities that only surface under extreme conditions. The broader safety impact of Flight 32 extended beyond the Airbus A380 fleet. It reinforced global standards for engine monitoring, real-time diagnostics, and maintenance inspection protocols. It also strengthened training programs focused on abnormal situation management, ensuring that pilots remain focused on fundamental flight control even when confronted with overwhelming system failures. Ultimately, Qantas Flight 32 is remembered not as a disaster, but as a demonstration of resilience under pressure. It shows that while technology can fail in unexpected ways, disciplined human response can still prevent catastrophe. But it also delivers a warning. When verification is replaced by assumption, whether in engineering, automation, or decision-making, the expert trap is already in motion. There's a final, chilling photo taken by a passenger on the ground in Batum that shows the exact millisecond the turbine disc exited the engine casing. To see the forensic analysis of that image, watch this video next. It shows the true power of a tiny crack.